Congruent triangles 6.3 SSS and SAS, and 6.4 ASA, AAS, and HL. For our warm-up, triangle ABC is congruent to EDF. Find X. So 2x plus 6 is along our side link CA or AC. So when I look up at my letters, AC must correspond to EF. So that means that it corresponds to 14. So then 2x plus 6 equals 14, minus 6, 2x equals 8, and finally x equals 4. On our next problem, it's asking us to use the figure below, list the variables in order from least to greatest. So what I've done is I've added all the angle measures between the two triangles. Then what you should do is order the two lengths by size per triangle. They only share one side length, so we really need to know where does E fall into the equation here. So on the left-hand triangle, E is the smallest because it's across from 30, then D because it's across from 50, and A is the biggest because it's across from 100. Do the same thing on the right. C is the smallest, B is the middle, and E is the longest. So E is the longest side between the two on the second triangle, but it's the shortest side on the first triangle. So what we're really saying is that E is less than D and A, but E is greater than B and C. So in our statement here, E essentially has to go in the middle. So E is less than D is less than A, but E is greater than B and greater than C. So all in comparison to side E. All right, so our first triangle congruence pattern that we're learning today, what is the minimum amount of information that you can know between two triangles to say that they're congruent? Do you have to know that they're congruent polygons? Do you have to know that they have all the same angles and all the same sides? And the answer is no. The minimum amount of information that you need to know is 3 pieces of information, and there are several patterns that we're going to learn. The first one is the side, side, side pattern. So if you have two triangles, I shouldn't have drawn it so right, but that's okay. If you have two triangles and you want to for sure say that these are two congruent triangles, then they need to have 3 sides that are congruent. I like to use little S's around the triangle so that I can see side, side, side. So that's what SSS stands for, side, side, side. And we're going to use it to write some proofs. Example number 1, ABC is a parallelogram, and we'd like to prove that triangle ABC is congruent to triangle CDA. So when you see proofs like this where you're trying to prove that triangles are congruent, it's a good idea to try to go for one of the triangle congruence patterns. So I'm going to draw my picture over here. So ABC D is a parallelogram, so that means opposite sides are parallel, and that also means that opposite sides are congruent. So there's some sides, and then it wants us to say that ABC is a triangle. So the thing that we're going to have to add on here is that diagonal AC in order to see our triangles. So we've got a side, and then the third side is going to be this AC. What's going to happen here is that that's a shared side between these two triangles. So ABC is congruent to CDA by side, side, side. So now we're going to write our proof. You can write it as a flow proof or a 2-column, whichever you prefer. I'm going to write it as a flow proof. So ABCD is a parallelogram. And that's given. Then if it's a parallelogram and we're trying to prove something about side, 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 what we need to talk about are the sides. So AB and CD and BC and AD. So we can say AB is congruent to CD and BC is congruent to AD. And we knew that by the definition of a parallelogram. Then the last one that we needed to add onto the picture was AC. So that's actually something you need to include in your proof. So you call it draw AC. That's what we did. We drew an AC, and the reason you're allowed to do that is because through any 2 points, is a line. Then what we're trying to say is that AC matches AC between the 2 triangles. So we can say AC is congruent to AC. And if you recall, that's by the reflexive. Reflexive property. Now we've got a side statement, a side statement, and a side statement. So now I bring these 2 together. We can say triangle ABC is congruent to triangle CDA, and that's by our new postulate that we just learned up above, by side, side, side. And you can just use SSS to say that. All right, let's learn several more triangle congruence pattern. The first thing we need to know is what's an included angle. An included angle is an angle of a polygon whose vertex is shared points of 2 sides of the polygon. So what you should think about is that this is between the 2 sides. An included angle is between 2 sides. So if I had a picture, you know, that would be my included angle between those 2 sides. So the next one we're going to learn is side angle side, SAS postulate. If 2 sides in an included angle, that's key that it's an included angle, of a triangle are congruent to 2 sides of the included angle of another, then the triangles are congruent. So let's draw an example. So you have to have a side, so let's pick a side to be congruent. Then you choose an included angle, so whichever one you want. I'm going to choose this top one. So that one's congruent. So that means that the next line that I have to choose is the one that matches that vertex. So these 2 sides must be congruent. So this is a side and an angle and a side. As I go around the triangle, order does matter. But you can go either way, and it's SAS or SAS, either direction. So example number 2, NO is congruent to NQ, and NP bisects ONQ. So that means that this angle is congruent to this angle. So now I've got a side and an angle, and now I just need this third side, or this third piece of information, but second side. So we're going to do the same thing we did on the last one, where we're going to say that NP is a shared side between the 2. You can call it reflexive property or shared side. That's really what's happening there, is that they share that side. All right, let's do another flow proof. So NO is congruent to NQ, and NP bisects angle ONQ. That's given. And it actually gave me a lot of information. It gave me a side and an angle. So the only thing that I'm lacking is this other side. So now that bisects, we can talk about the angle part. So angle ONP is congruent to angle PNQ. That's by the bisector, definition of a bisector. Then we're going to say NP is congruent to NP by reflexive. And now I've got my information, a side and an angle and a side. So now I can bring these all together. So that one comes over, that one comes over, and that one comes over to say that triangle NOP is congruent to triangle NQP, and that's by side, angle, side. All right, the last one we're going to do a proof for today is angle, side, angle. An included side is a side of a polygon whose endpoints are the vertices of two angles of the polygon. So if I had something like this, let's do, like, I'll even do like this. So these two angles are congruent, and that would be the included side that's between them. So you're looking for a side that's between two angles. So what does it look like on the triangle patterns? So you have your angle and your side and your angle, and your angle and your side and your angle, angle, side, angle. So let's write the proof for this one, or use this in a proof for this guy. Oops, dropped my paper. Okay, so it says, given that HK bisects JHL, so that's down here, that's saying that this angle is congruent to this angle. And KH also bisects JKL, so these two angles are congruent. And we're trying to prove that the two triangles are congruent to each other. So the last piece that you're missing is the included side. So once again, the shared side comes into play, and that KH is congruent to KH to get us a shared side length between the two of them. So here we go. HK bisects angle JHL, and KH bisects angle JKL. That was given. Then we can say that these angles are congruent. So angle KHL is congruent to angle KHJ, and angle HKJ is congruent to HKL. Those are by the definition of a bisector. Then we've got our shared side length, our reflexive properties. So KH is congruent to KH by the reflexive property. And then we bring it all together. Two angles and a side. So then triangle JHK is congruent to triangle LHK by angle, side, angle. So then the last one, we're not going to write a proof for this one. Well, the last one of the kind of traditional ones is angle, angle, side. If two angles and a non-included side are congruent to the corresponding parts of another, then the two triangles are congruent. So take a look at our example here. Which one of these are congruent and which ones are not? They all kind of look congruent, but there is one of these examples is false. So the way that you need to check is actually watch where the angles are. So 1, 2, side, 1, 2, side, 1, 2, side, 1, 2, uh-oh, not the side. So see how EK is on the side length between the one arc mark and nothing? And look here, that would have been AC on this one, ED on this one, and AC on this one. So this example is not an example of AAS, but this one is. So those two triangles are congruent to each other by angle, angle, side. Then the last congruence property is hypotenuse leg. Hypotenuse leg is specifically for a right triangle. That's key here, that we're working with right triangles. So let's draw our pictures. We've got two right triangles. And what has to be true is that the two hypotenuses have to match and one leg. Now, this is an example of ASS, but this is the only form, or if you go the other way, SSA, this is the only form of SSA that works. So recall that there's no bad words in math and there's no bad words in triangle congruence. That's the only triangle congruent shortcut that does not work is the bad word one. Thank you.